Welcome back to the Deep Dive. Today we're really getting into the weeds of cutting-edge AI. We're looking at large language models, LLMs, and how they're making, well, pretty remarkable strides in complex reasoning.
Absolutely. Things like advanced math, complex coding problems, logical deduction. These are areas where LLMs are really starting to shine, aren't they?
They really are. But here's the thing. The puzzle that's been, frankly, a bit frustrating for researchers, even with all this power, what's stopping these models from really learning from experience at scale, through reinforcement learning, RL?
Right. That's the million-dollar question, or maybe $1 billion question given the compute costs. We see these amazing capabilities, but scaling up RL, which is how they should learn from trial and error, has hit this persistent wall.
A wall is a good way to put it.
Yeah.
And it's not just some minor bug, right? It's a fundamental technical challenge.
Exactly. Researchers have pinned it down. They call it policy entropy collapse. And what's really striking, maybe even a little unsettling, is just how, well, predictable it is.
Predictable. That's the word that jumps out. So, okay, our mission today is to unpack this whole thing. We'll look at why it's predictable, dig into the mechanisms underneath it all.
And then the exciting part, we'll look at some really ingenious new techniques that researchers have developed to actually overcome this bottleneck.
And just to set the stage, as always here on the Deep Dive, we're focusing squarely on the technical stuff. The details, the implications for the tech itself, how it works, why it breaks, how we fix it. We're sticking to the engineering and the science today.
Yep, pure tech focus. And our main guide for this is a really groundbreaking research paper. It's titled The Entropy Mechanism of Reinforcement Learning for Reasoning Language Models. It lays out the problems and, crucially, the solutions we're going to talk about.
So think of this as your shortcut, your deep dive into the key takeaways from that technical work. Ready to jump in?
Let's do it. Where should we start? The core concept, maybe. Policy entropy.
Yeah, let's start there. Because when we talk about learning from experience, RL, this term policy entropy keeps coming up. It sounds critical. What exactly is it?
Okay, so policy entropy. At its core, it's a measure. It quantifies the, let's say, randomness or uncertainty in the AI's action selection. Think about an LLM generating text. At each step, it has choices for the next word or token.
Right, a whole distribution of possibilities.
Exactly. A policy with high entropy means the AI is spreading its bets, so to speak. It's assigning probability more evenly across many different options. It's exploring. It's like trying out lots of different paths.
Okay, exploratory mode and low entropy.
Low entropy is the opposite. The model becomes very certain. It assigns very high probability to just one or a few actions and very low to everything else. It's zeroed in.
Yeah.
It's exploiting what it thinks is the best path based on what it's learned so far.
So high entropy means exploration, keeping options open. Low entropy means exploitation, sticking to the known good stuff.
Precisely. And that leads directly to this fundamental balancing act in RL.
The classic exploitation-exploration trade-off. I feel like we talk about this a lot in AI.
Because it is central. An agent has to constantly juggle these two things, exploit what works now to get rewards, but also explore new, potentially better strategies for the long run. Policy entropy is basically the knob that controls exploration.
So if that entropy knob gets turned down too low too fast,
Then exploration stops. The model gets stuck. It might find a decent solution, sure, but it won't find the best one if that requires trying something new. It stops innovating, essentially. It gets locked into a local optimum.
and this is where the trouble starts for LLMs and RL, according to this paper. They describe this really consistent, maybe even concerning pattern. What did they observe?
They observed this policy entropy collapse, and it's not a gentle decline. The paper states that policy entropy sharply declines to near zero in a few training steps.
A few steps, that sounds incredibly fast.
It is. Imagine the LLM starts out considering, a decent range of responses, but very, very quickly it narrows down to maybe one or two highly probable sequences. It becomes extremely certain.
Wow. So the model just slams the door on exploration almost immediately. And what does that do to its performance? Does it just get super specialized but limited?
That's the kicker. This rapid drop in exploration, this premature certainty, it's always linked to performance saturation. The model's accuracy, say on validation tasks, shoots up initially.
Which sounds good.
Right, it looks promising at first, but then it just hits a hard ceiling, it plateaus, it stops getting better, even if you keep training it for much, much longer.
So it finds a solution, maybe an okay one, but then it just gives up looking for anything better because it's become too certain, too narrow in its thinking.
That's exactly it. It self-limits its own potential because the entropy collapses, shutting down the search for superior strategies.
That seems like a massive problem if you're aiming for peak performance, especially on really hard tasks.
Yeah.
And the paper quantifies this, right? They have numbers on how fast this happens.
Oh yeah, the numbers are stark. They found that over 95% of the entropy drop and over 95% of the performance gains happen right at the beginning of training.
95%. That early.
Get this, 73% of the total entropy lost the exploration drying up, and 76% of the total performance gain happen in just the first 200 gradient steps. And these training runs often go for, say, 2,400 steps.
Okay, wait, let me get this straight. In the first, what is that, like 8% of the training time? Less than 10% anyway. In that tiny fraction, you get 3/4 of the improvement and lose 3/4 of the ability to explore.
Precisely. The vast majority of the learning and the entropy loss is crammed into that very initial phase.
That sounds incredibly inefficient.
Yeah.
What happens in the rest of the training then?
Well, it gets even more striking. If you look at the first 800 steps, that's still only about a third of the total training that accounts for over 93% of the performance gain and 94% of the entropy loss.
So for the remaining 2/3 of the training, the last 1,600 steps or so,
Yeah.
you're getting almost nothing.
Marginal returns, that's the term they use. You're burning massive amounts of compute, time, energy for tiny, almost negligible improvements because the model has effectively stopped exploring. It's locked in.
Wow. Okay. That paints a very clear picture of a fundamental bottleneck.
Yeah.
It's not just a feeling, it's measurable and predictable.
And that predictability is key. It led them to discover what they call an empirical law.
An empirical law. That sounds serious, like something fundamental they uncovered.
It really is. They found this surprisingly elegant quantitative relationship. It connects the validation performance, let's call it R, with the policy entropy, H, and it fits a simple exponential function.
An equation. Okay, what is it?
It's RAXPH plus B.
RAXPH plus B.
Yeah.
Okay, R is performance, H is entropy. What about A and B? What do those coefficients mean?
So A is really interesting. It represents the rate at which the model converts entropy or uncertainty into performance. Think of it as the efficiency of trading exploration for reward.
So a higher A means it trades uncertainty for performance more aggressively.
Exactly. And B sort of sets the scale, helps define the maximum potential. But the crucial insight here is what this equation implies about the maximum performance.
What does it imply?
The maximum performance, the ceiling, occurs when entropy H goes to 0,
Right.
when exploration is completely gone. At that point, XPH becomes XP0, which is 1. So the performance R just becomes A plus B.
Ah, so the equation itself predicts a hard performance limit that's reached when entropy is exhausted.
Precisely. It formalizes that trade-off. The policy, predictably, almost deterministically, trades its uncertainty for rewards until it runs out of uncertainty and hits that performance ceiling defined by A and B.
And this isn't just a neat mathematical observation. This has huge practical implications for scaling RL with LLMs, right? Like how we even approach training.
Massive implications. First off, predictability. This law means you can potentially predict an LLM's final RL performance much earlier in training. Well, they showed this with the Quinn 2.5 models. They took models from 0.5 billion up to 32 billion parameters by fitting this R versus H function using only the first 36 training steps.
36 out of 2,400. That's like 1.5% of the training.
Exactly. Using just that tiny initial snapshot, they could predict the performance for the next 200 steps with incredibly low error, like 0.9% average error for math tasks, 1.2% for coding.
It's amazing prediction accuracy from such early data.
And predicting the final step performance was even more accurate, 0.5% error for math, 1.9% for coding. Think about what that means for resource allocation.
It means you could potentially stop incredibly expensive training runs super early. If you see they're headed for a performance ceiling you don't like, you could save huge amounts of compute.
Millions of dollars, potentially. It's like an early warning system for hitting that wall. No need to run the full course if you know it's not going to reach the destination you want.
That's a game changer for managing large-scale AI projects. What's the second big implication?
The second follows directly from the law itself. The existence of that performance ceiling tied to entropy exhaustion. It gives us a mathematical reason why simply throwing more compute power at RL training for LLMs often yields diminishing returns.
Right. If the entropy has already collapsed, more training steps, more GPUs, it doesn't matter much. The model isn't exploring anymore anyway.
Exactly. Scaling compute becomes marginal unless you address the entropy problem itself. You're just pushing against a locked door harder.
So More compute isn't the silver bullet. That's a crucial takeaway. What about those coefficients, A and B? Did they change depending on the specific RL algorithm used?
This is another fascinating finding. They found that A and B are largely algorithm irrelevant. They tested different RL algorithms, GRPO, RLOO, prime, and the coefficients remained consistent for a given model and task.
Whoa, so it's not just an artifact of how you train it.
Seems not. It suggests these coefficients capture something more fundamental, something intrinsic about the model itself and the data it's trained on, rather than the specific optimization technique. It points towards inherent properties of the LLM's learning dynamics.
That strengthens the idea of this being a fundamental law for these models.
Yeah.
And did this law, these coefficients, scale predictably with the size of the model?
Yes, and this is maybe one of the most powerful parts. They discovered a log linear relationship between the model size, parameter count, and these coefficients A and B.
Log linear, so as the model size increases exponentially, the coefficients change linearly on a log scale.
Sort of, yeah. It means there's a predictable mathematical relationship, and the implication is huge. You can potentially extrapolate the A and B coefficients and thus the performance ceiling for larger models based on the training dynamics you observe in smaller models.
Wait, are you serious? You could train a smaller, cheaper model, observe its entropy collapse and performance curve, calculate its A and B, and then use this scaling relationship to predict the likely performance ceiling of a massive, hypothetical future model without having to actually train that massive model with RL.
That's the potential breakthrough here. It extends predictability from just training time to the dimension of model size. Imagine estimating the potential of a 100 billion or trillion parameter model based on data from a 10 billion parameter one. It could revolutionize how we plan and resource AI development.
That's mind-blowing, frankly. It sounds almost too good to be true, like an AI crystal ball.
It's definitely a powerful predictive tool they've uncovered. Now, one technical point the paper maybe doesn't hammer on but is important is the practical side. Actually monitoring this stuff, calculating entropy and performance constantly, fitting these curves in real time during a massive training run. That itself has a computational cost, right?
Good point. The prediction is valuable, but implementing the monitoring system efficiently at scale is another engineering challenge.
Definitely. But the predictive power itself is a huge leap.
Okay, so this whole discussion about a predictable ceiling really feeds into that ongoing debate, doesn't it? The one about whether RL is just, eliciting latent behaviors already learned during pre-training, or if it's genuinely teaching the model new things.
Yes, the elicitation versus learning debate. It's a big one. And this research adds a really interesting angle. It sort of says, yes, there is a ceiling if entropy collapses. It acknowledges that observed limitation.
But there's a but, isn't there?
Yes, a crucial but. The paper argues strongly that the ceiling isn't an inherent limitation of RL itself. It's not that RL can't teach the model new tricks beyond pre-training. The problem is the specific entropy mechanism of LLMs that forces this premature collapse, hindering exploration.
So the ceiling exists because the LLM's internal dynamics shut down exploration too early, not because RL is fundamentally incapable of pushing beyond the pre-training baseline.
Exactly. The potential might be there, perhaps unlocked by the pre-training, but the RL process, as it typically unfolds with LLMs, gets stuck before it can fully realize that potential due to this entropy collapse. It's like having a brilliant student who just stops trying new approaches after finding one decent answer. The capability is there, but the learning process gets short-circuited.
That makes a lot of sense. It shifts the blame from RL itself to the interaction between RL and the specific way LLMs seem to operate internally, which perfectly sets up the next big question. Why does this happen? What's the mechanism driving this consistent, steady decrease in entropy?
Right. We know what happens to collapse. Now let's unpack the why. The paper dives into the theoretical dynamics here, and it comes down to how LLMs work as softmax policies.
Softmax policies, meaning how they convert their internal scores into probabilities for the next token.
Exactly. The model produces these raw scores, called logits, for every possible next token. Higher logit means higher confidence. The softmax function then turns these logits into a probability distribution, summing to 1.
Okay, standard stuff for LLMs. How does that relate to entropy change?
Here's the key theoretical finding. They call it lemma 1. It says the change in policy entropy from one training step to the next is approximately equal to the negative covariance between two things.
Negative covariance.
Yeah.
Break that down for us. Covariance of what?
It's the negative covariance between, first, The log probability of taking a certain action, like
Hmm.
picking a specific next token. And second, the change in the logit for that same action during that training step.
Log probability and the change in the logit. Hmm. Can you give an intuitive feel for that? What does positive covariance here mean?
Okay, let's make it concrete. Covariance just measures if two things tend to move together. Positive covariance means when one goes up, the other tends to go up too. So imagine an action, say, generating the word therefore. If this action already has a high probability, the model likes it, and its logit increases in this training step, the model becomes even more confident.
Then those two things are moving together. High probability and the confidence is increasing.
Exactly. That's positive covariance between the log probability and the logit change. Now remember, the entropy change is the negative of this covariance.
Ah. So if you have strong positive covariance, the model getting more confident about things it already likes, that translates directly into a decrease in entropy.
You got it. The model is essentially reinforcing its existing preferences. I liked this action, it turned out well, implicitly, as RL updates logits based on rewards advantages, so I'm going to like it even more. This feedback loop drives certainty up and entropy down.
It's like a confirmation bias loop baked into the learning dynamics. And how do the RL algorithms actually cause these logit changes?
That's the next piece. The change in the output logits is directly determined by the RL algorithm you're using. The paper shows for standard algorithms like policy gradient theorem 1 and natural policy gradient theorem 2, this change in logits is proportional to something called the action advantage.
Action advantage. That's basically how much better an action was than expected, right?
Mhm.
Like the reward you got versus some baseline.
Precisely. It measures the goodness of an action relative to the average or expected outcome. So, putting it all together.
If actions the model already favors, high probability, consistently turn out to be good, high advantage, this leads to increasing their logits, creating positive covariance.
Which, because of the negative sign in the lemma, leads to a decrease in entropy. It's a clear chain. High probability actions proving advantageous leads directly to reduced exploration.
Okay, that theoretical chain makes sense. Did they back this up with experiments? Did they actually measure this covariance and see if it matched the entropy changes?
They did, and the empirical results are very convincing. They used a 7B parameter Quinn model on math problems with the GRPO algorithm. They set it up as a bandit setting. The prompt is the state, the whole generated answer is the action. This makes measuring the covariance easier.
Smart simplification. And what did the graphs show?
The graph showed the negative entropy difference and the measured covariance term tracking each other very closely. They exhibit highly similar dynamics, as the paper puts it.
So when entropy was dropping fast early on,
The measured covariance was large and positive, exactly as the theory predicted. It visually confirms that the model quickly finding and reinforcing high probability, high advantage actions is what drives that initial sharp collapse.
and later in training, when the entropy decrease slowed down.
The covariance also stabilized, but crucially, it remained positive throughout the training. Even if it got smaller, it was still positive, still pushing entropy down, albeit more slowly. This explains the persistent, albeit slower, decrease in entropy later on. The certainty mechanism keeps running.
That's really solid empirical validation for the theory. Did they notice anything else about this covariance? Like, did it change based on how hard the math problems were?
Yeah, that was another neat finding. For easier prompts where the model was getting high accuracy, the covariance was higher.
Meaning, for easy stuff, it was more confident, found good answers quickly, and doubled down harder, reducing entropy faster for those cases.
Exactly. Its confidence was well calibrated for the easy stuff. It could safely exploit those high confidence paths.
And for the harder examples.
There, the covariance was lower. This suggests that for difficult problems, the actions the model thought were high probability weren't reliably leading to high rewards or advantages. Its confidence wasn't as well calibrated.
So it was less sure about which high probability actions were actually good, leading to less reinforcement of those paths and slower entropy reduction.
Right. It implies the model struggles more to identify consistently advantageous strategies for hard problems, which results in a weaker positive covariance and thus less aggressive entropy collapse in those specific cases. But the overall trend across all examples is still positive covariance driving entropy down.
Okay, this gives us a really clear picture of the why. Now, the crucial part, the solution. If this covariance mechanism is the driver, can we target it? We know traditional entropy regularization methods didn't work well for LLMs.
Right, that's key. Simply adding an entropy bonus or a generic KL penalty didn't cut it. The entropy loss was too sensitive, often exploding or doing nothing useful. The KL penalty stabilized entropy but hurt performance. They just weren't the right tools for the specific problem.
So what is the right tool, according to this research? How do you fix it?
The insight comes directly from the analysis. If high covariance tokens are the main culprits driving the collapse, then the solution is to limit the step sizes of high covariance tokens. Target the troublemakers.
Why focus just on those specific tokens? Are they really that dominant?
Overwhelmingly dominant. Remember those numbers. The top 0.02% of tokens had a covariance orders of magnitude higher than the average. A tiny fraction of tokens is responsible for the vast majority of the entropy-reducing pressure. These outliers take a dominant part in triggering the entropy collapse.
It's like a few bad apples spoiling the bunch in terms of exploration. So how do you limit their influence? This led to the new methods, Clip-Cov and KL-Cov.
Exactly. Let's take Clip-Cov first. The name gives a hint. It literally clips a small fraction of high covariance tokens out from policy gradient updates.
Clips them out. How does that work in practice?
It's quite targeted. In each training step, they identify tokens whose covariance falls within a specific high range, say between 1 and 5. Then they randomly select a very small fraction of these high covariance tokens, maybe a ratio R of 2 by 10, 4, so 2 in 10,000.
Okay, so you've identified the specific problematic token instances. What's the clipping part?
The key action is these selected tokens are detached from the policy gradient. What that means technically is, during the backpropagation phase, where the model calculates how to update its weights, the gradient signals coming from these specific clip tokens are essentially ignored, set to 0.
So their overly strong signal, driven by that high covariance, just doesn't get factored into the model update. You surgically remove their influence on that step.
Precisely. You stop those outliers from dominating the update and collapsing the entropy for everyone else.
Clever. Okay, and what about the other method, KL-Cov? Is it similar?
Conceptually similar goal, control the outliers, but a different mechanism. KL-Cov is maybe a bit simpler. Instead of detaching, it applies a KL penalty, but only to the tokens with the very highest covariances.
So it's not completely ignoring them, but penalizing them if they get too confident.
Sort of. It identifies the tokens in the top K% of covariance values. For example, top 0.2% for a 7B model, maybe top 0.02% for a 32B. Then, for only these tokens, it adds a penalty term. This penalty is the KL divergence between the current policy's probabilities for these tokens and the probabilities from a recent rollout policy.
So it encourages these high covariance tokens not to stray too far too quickly from where they were recently. It dampens their rapid certainty gain.
Exactly. It regularizes their updates specifically, using a tunable coefficient beta to control the strength of that penalty. It's a softer touch than Clip-Cov, perhaps, providing a more continuous form of control.
Okay, two different surgical approaches to targeting the high covariance culprits. Clip-Cov detaches them, KL-Cov penalizes them. Did they work in practice? What were the results?
The results are really the headline here. They tested these on Quen 2.5 models doing math reasoning, comparing against the standard GRPO baseline and another technique called Clip-Hire.
And the outcome, did they get better performance?
Yes, significant improvements. Both Clip-Cov and KL-Cov showed non-trivial improvements across all benchmarks. For the 7B model, about a 2.0% average improvement over the baseline.
Okay, 2% is nice. What about the big 32B model?
That's where it got really impressive. For the 32B model, the average improvement was a much more substantial 6.4%. And on the really tough benchmarks, like the AIM math competition problems, the gains were huge, 15.0% improvement on AIME 24, 14.6% on AIME 25 for the 32B model using these methods.
15%. On AIM-level problems, that's not just non-trivial. That's a massive leap in reasoning capability.
It really is. It strongly suggests these methods are unlocking significant potential, especially on complex, multi-step reasoning.
And critically, did they solve the original problem? Did they maintain higher entropy? Did they stop the collapse?
Yes, that's the other key part of the results. Both methods were able to maintain a considerably higher level of entropy throughout training. They effectively prevented the collapse, allowing for sustained exploration. You could see the entropy curve staying much, much higher compared to the baseline, which just tanked.
So the mechanism worked. Higher entropy, sustained exploration, leading to significantly better performance, especially on hard tasks.
Exactly. The connection is clear. By managing the entropy, they enabled the model to keep searching and find better solutions it would have otherwise missed.
Did they notice any other effects? You mentioned the baseline models plateaued quickly. Did these methods show more continuous learning?
Well, related to sustained exploration, they noticed something interesting. The models trained with Clip-Cov or KL-Cov tended to incentivize longer responses.
Longer responses. Why is that significant?
It suggests the model isn't just finding the quickest, maybe superficial answer. By exploring more, it might be finding more detailed step-by-step reasoning paths, which often require longer explanations or calculations, especially in math or code generation. It points towards more thorough problem solving.
That makes intuitive sense. More exploration leads to potentially more complex and complete solutions. And were these methods stable? Some regularization can make training jittery.
They reported good stability. Unlike the clip-higher baseline, which they said became unstable and saturated, Clip-Cov, and especially KL-Cov, provided more stable entropy curves throughout training. Stability is crucial for these huge training runs.
Definitely. And you mentioned the gains were bigger for the larger 32B model. What's the interpretation there? Why would larger models benefit more?
The inference is really interesting. Larger models have vastly more knowledge baked in from pre-training, right? More parameters, more data seen. They likely have greater potential from pre-training.
Okay, a bigger reservoir of latent knowledge.
So the theory is, once you remove the exploration curse, once you stop the entropy collapse using Clip-Cov or KL-Cov, these larger models are much better positioned to actually use that vast latent knowledge. They can explore a richer space of diverse and higher quality policies that were previously inaccessible because they got stuck too early.
It's like these methods unlock the pre-trained potential that was being held back by the RL dynamics, fix the bottleneck, and the bigger engine performs much better.
That's a great analogy. The methods allow the RL process to actually leverage the scale of the underlying pre-trained model more effectively.
And it seems like these methods give researchers actual control knobs for entropy.
Yes, that's a really valuable aspect. For Clip-Cov, you can tune the ratio R of clipped samples, clip more, get higher entropy. For KL-Cov, you adjust the penalty coefficient beta. Higher beta generally leads to higher, more stable entropy.
So you can actually try to steer the level of exploration? That's powerful.
It is. While the paper admits that the optimal value of entropy under different scenarios remains an open question, we don't have a magic number, yet having the ability to steer entropy is a huge step forward. It lets researchers experiment and potentially tailor the exploration level to the specific task or phase of training.
It moves from just observing the collapse to actively managing the exploration-exploitation balance. Of course, there's still that practical question you raised earlier, the computational cost of calculating all those covariances in real time for every token.
Right. That's an important engineering consideration for scaling this up. The paper demonstrates the principle works and is effective, but optimizing the implementation for truly massive scale is likely the next step.
So stepping back, what's the kind of the philosophy here? It feels like it's about precision, not brute force.
Absolutely. The core idea is that you can manage the entropy dynamics of these massive complex systems by intervening on a tiny, tiny fraction of the components, those pivotal high covariance tokens. We're talking 1 in 1,000 or 1 in 10,000 tokens.
So it's not about adding some global penalty everywhere, but identifying and managing the few key points of leverage that dictate the overall system behavior.
Exactly. It suggests that the entropy dynamics, at least the collapse part, are driven by these specific outliers. Control them, and you can reshape the entire learning trajectory, enabling sustained exploration without destabilizing the whole process. It's surgical.
This really ties everything together nicely. We started with this problem, LLMs are great, but struggle to learn effectively via RL at scale. We saw the predictable entropy collapse.
Understood the why, that covariance mechanism where models get overconfident about high probability actions that prove advantageous.
And now we have these targeted solutions, Clip-Cov and KL-Cov, that directly address that mechanism by managing the outlier tokens, leading to maintained exploration and significant performance boosts, especially for larger models on complex tasks.
It's a really coherent story, from problem identification through mechanistic understanding to effective, targeted solutions. A real piece of detective work in AI research.
Absolutely. And it loops back to that bigger picture you mentioned earlier. RL is seen as this crucial next scaling axis for LLMs, the way they'll really advance beyond just absorbing data during pre-training.
Right. But this research shows that just throwing more compute at RL isn't enough. You hit that entropy wall. Scaling RL effectively requires intelligent entropy management. You need to keep the exploration alive.
Otherwise, like your analogy, you have these incredibly powerful engines, these massive pre-trained models, but they're stuck driving in circles because the RL process itself shuts down their ability to navigate new paths.
Precisely. By mastering this entropy mechanism, by learning how to control it, we're not just tweaking performance numbers.
Right.
We're potentially unlocking a more fundamental capability for exploration and discovery within these models.
Pushing them towards maybe a higher level of intelligence where they can genuinely find novel solutions, not just refined versions of what they saw in pre-training.
It really makes you wonder, doesn't it? If we can reliably prevent this premature certainty, if we can keep these models exploring effectively throughout their learning process, what becomes possible?
What new kinds of complex reasoning, problem solving, maybe even creativity could emerge when these LLMs are freed from this exploration curse? When they can fully leverage their vast knowledge in truly adaptive ways.
That's the exciting frontier. It suggests that the path forward involves not just bigger models, but smarter training dynamics, actively managing things like exploration to unlock their full potential.
A really provocative thought to end on. Imagine LLMs that don't just plateau, but continuously find better and perhaps entirely unexpected ways to solve problems.
The potential is certainly there, and understanding these underlying mechanisms, like the entropy dynamics, is key to unlocking it.
Well, that brings us to the end of another deep dive. We really hope this exploration into the entropy mechanism and how to manage it in LLMs using RL has been insightful for you. Maybe even spark some new ideas. As always, we focus on the technical details here. If you want to keep up with the latest AI and ML research papers that we often discuss, definitely check out our webpage. The link is right there in the bio.
Yeah, lots of exciting stuff happening constantly. Thanks for joining us.
Until next time, keep exploring.